By now we should be quite practiced at balancing chemical reactions. But now we're going to take it up a level, go one step further. We're not only going to balance things, but we're going to predict the products of a reaction given to reactants and then balance it. The type of reaction we're going to focus on right now is called a double displacement reaction, when you're reacting together two ionic compounds, or acids can also be in there. We know acids behave a little funny, somewhere between ionic and covalent compounds, so since they ionize, we're sort of lumping them in here. So given two ionic compounds, or an ionic compound and an acid, how would you predict the products? So we symbolize these A, B, C, D, where each A, B, C, D piece stands for an ion, and we can follow just a few simple steps. The first thing you do is swap partners to predict products. So I like to say the outsides go together and the insides go together. So let's say I had NaCl plus silver nitrate, and I wanted to predict what they would form. So I would put the outsides together and I would put the insides together. So when I put them together, I always put the positive thing first, and I must always consider the charges when you put your ions together. Now this one's easy because sodium's +1, chlorine's -1, silver's +1, nitrate's -1, so these are going to pair up nicely, but we'll see when we do another example that that's not always the case. So we predict our products, so we'll put the sodium is +1, nitrate is -1, so they go together, 1 and 1. And then silver is +1, chlorine is -1, so they also go together, 1 to 1. It's not always the case, but we'll do it an easy one to start with. So we put the positive ion first every single time and put the outsides and insides together. Now we determine if the products are solid, liquid, gas, or aqueous. Usually you're just choosing between these two options. So if you end up with an ionic compound, you're just going to check your solubility rules. So if I check my solubility rules, sodium, for instance, is always soluble, as is nitrate. So that's going to be aqueous. However, if I check my solubility rules over here, I find that chlorine is usually soluble, except when it pairs with silver. So it's insoluble. That's going to make this a solid. So we use solubility rules to determine if it's solid or aqueous. Now sometimes one of your products will be water, and that's always a liquid. That's basically the only liquid that you're going to get. So if you see water, it's a liquid. Otherwise, you're not going to have any liquids. There are also 4 products that can produce a gas. If you produce H2S, that's always a gas. If you produce H2CO3, that's going to break apart to form liquid water and CO2 gas. 2 other compounds will do a very similar thing. H2SO3 will also break apart and immediately form water and SO2 gas. And ammonium hydroxide will always break apart and form, let's make a theme here, water and a gas. Notice in each one of these 3, it broke apart into H2O, and then whatever was left was my gas. So H2CO3 made water and CO2, H2SO3 made water and SO2, NH4OH makes water and NH3. So those are the only 4 gases you're going to have right there. So liquid would only be if you see water, gas is if you see one of these 4 pieces, otherwise it's going to be solid or aqueous, and then you check your solubility rules. If you check your solubility rules and both your products are aqueous, basically no reaction has occurred. If you did the net ionic equation for that, everything would just cancel out. So all you really did was mix some ions together, but nothing really reacted. Last thing, you're going to balance your equation. This one's easy. This one's already balanced, but we're going to see that's not always the case. So after you predict your products, determine if they're solid, liquid, gas, or aqueous, then you're going to finish up by balancing your equation. So I showed us a baby example there. Let's look at some more complicated ones. Okay, complete and balance the following reactions, and then we're also going to label what type of reaction it is. So we can see that these are both either ionic compounds or ionic compounds with acids. So we're going to use our rules. Outsides go together, insides go together. It can be useful to decide where you're going to split your compounds. So the first one is an acid, so I'm going to split it right after the H. The second one is ionic because it has a metal, so I'll split it right after the metal. So that can help me figure out which pieces go together. Then I'm going to use charges to figure out how they pair up. So first pairing, I have H plus, and I have HSO3 minus, plus 1 minus 1. They just directly pair up. But I'm going to simplify this and write H2SO3. Oops, don't know what that is yet. Now I'm going to write my other product. So second one, I have Na, which is plus 1, and acetate, C2H3O2 minus 1. So again, those just directly pair up. Nice and easy. Now that I figured out my products, I'm going to go back and look at solubility rules, decide if I have solid, liquid, gas, or aqueous. H2SO3, I should memorize that one. That one I know immediately breaks apart and makes liquid water and SO2 gas. So I just cross that out and write out what I know he turns into. So instead of H2SO3, it's going to be H2O and SO2 gas. So I know those. Then I look at my sodium acetate. Both of those are always aqueous, so this guy's going to be AQ. If I check, he's already balanced, so that means I'm done with this one. So swap partners, predict products, and check their phases, and then make sure it's balanced. All right, I'm going to clear this out so we have room for our second guy here. Hydrobromic acid with aluminum hydroxide. So again, we'll make a little mark about where we split. Outsides go together, insides go together. So let's look at how they pair up. First I have an H plus, and then I have an OH minus. I'm going to ignore this 3 for now. I don't necessarily need 3. I'm going to use the charges to figure out how they pair up, and then at the end, if I don't have the correct number of everything, I can balance it. So plus 1 and minus 1, these are going to pair up directly, but we're just going to call this water to make life easy. Right? HOH is just water. And now we'll pair up the insides. Aluminum has a charge of plus 3. Bromine has a charge of minus 1. So these are not the same, so I have to cha-cha him. I swap his charges, and I get AlBr3. Now water I knew was a liquid right away, but I don't know for him. I'm going to have to check my solubility rules. So now I've predicted my products. I'm going to go check my solubility rules. Bromine is pretty much always soluble unless it pairs with silver, mercury, or lead, which is not the case here. So this is going to be AQ. So I've swapped partners to predict my products. I used the charges to figure out exactly how they paired up, and I got my phases. So the last thing I need to do is balance. This reaction is not balanced right away. For instance, I have 1 bromine on the left, 3 bromines on the right. So I'm going to put a 3 right here. That fixes my bromines. However, now I have 6 hydrogens total on the left side, right? 3 from here and then 3 from here. There's only 2 on the right. So I'm going to put a 3 right here. And it turns out that also fixes my oxygens. 3 oxygens here, 3 oxygens here. So now we are balanced. So swap partners, use charges to figure out how they match up, check your solubility rules to get the phases, and then balance. That's it. Oh, one last thing. I forgot to determine what kind of reactions these were. So if we go back, we had liquid water, SO2 gas, and sodium acetate up here. He was aqueous. All right, so this first one, as soon as you see a gas, you know this is a gas evolution reaction. So if you produce a gas, it's going to be gas evolution. Second one, we don't have a gas. We don't have a solid. Solid indicates a precipitation reaction. So and we know it's not a combustion reaction. Combustion reaction means you have oxygen in there. So if you look in your products and you don't have a solid or a gas, you probably have an acid-base reaction. If you go back and look, yep, HBr is an acid. Aluminum hydroxide is a base. This must be an acid-base reaction. So in addition to predicting and finishing our reactions, we should be able to determine what type of reaction it is.